More whiteboard markers, I hope.
Yeah, well, yes, I am. I'll send you a box.
So
welcome back to the seminar, and we're happy to have Pavlo Pylyavskyy talk about crystal invariant theory.
Okay, hi everybody. Thank you so much for inviting me. So my talk is meant as a background for Gabe's talk. So Gabe's talk will be based on our joint work with Ben Brubaker and Travis Scrimshaw. But essentially, I will not get to any new stuff in my talk. I just want to remind you, and for some of you, of course, this will be already everything known, but for some of you, maybe not, and then it will be helpful. So I just want you to remind you some very basic things about crystals and how to lift them to geometric setting. Okay, so let's talk about basic SLN crystals, which is how I call just a single row crystal. What does it mean? It means a single row semi-standard tableau filled with numbers 1 through n. Can people hear me?
yes.
Yeah, everything okay? Okay. And crystal operators EI tilde. So operator EI tilde changes the last I into I plus 1. Okay, so here's a very small example. You can start with 1, 1, apply E1 tilde, you get 1, 2, apply E1 tilde, you get 2, 2. Any questions so far? This is how this particular crystal graph looks like. Any questions? So please.
Yeah, actually, my question is, can you apply E1 tilde again to 2, 2, and it's a no, and it just gives you 2, 2 again?
It will die. It will become 0. So all of those denote some vectors in some vector space, and if you apply it one more time, the vector just gets killed. So,
okay.
So you, in some sense, you cannot. This is where it ends. Okay, but yeah, I'll come back to it in geometric settings. There is an interesting difference with geometric setting. Okay, so now there is a general construction of tensor product of crystals. So in this case, I could define it in 2 different ways, because there is a very general rule due to Kashiwara of how to take tensor product of any crystals, not necessarily even those. But this would involve me explaining to you what are epsilon function and phi function of a crystal, which I might do at the end, but I don't want to do now. So an easiest thing to do is just to remember that probably many of you have seen this rule, that if you have a bunch of 1s and a bunch of 2s, then what you can start doing, you can start, you know, like let's say there was another 2 here. You can start matching the adjacent 1s and 2s, and then you'll be left with just a bunch of 1s and bunch of 2s. And then you can apply the same rule, just change the last I into I plus 1, or the last 1 into a 2.
So wait, so you're not matching up the final 1 and the final 2 because you don't have to match them up, or?
So, oh yeah, I have to match them. So in this case, there will be only one thing left, which is this 1. So my crystal operator would change this 1 into a 2. Does it make sense?
Yeah.
This is kind of.
I think you would match the 2s that come before the 1s, right?
Oh yeah, you're right. Sorry. Let's swap 2s and 1s. Okay. So 1, 1, 2.
Well, it all depends upon your tensor product convention.
Yeah. Okay. Nice to see my co-authors here, but yeah. So I was wrong. You are supposed to match 2s with 1s. That's how you're supposed.
So you need one more parenthesis. You need one more matching at the end.
One more matching, yeah. 2 more matchings. Yeah. Okay. So let me just show you what happens when you take tensor product kind of this guy with this guy, meaning this guy with himself, like the one I drew on the board. So it looks like a table, right? So let me draw it, and you will see what I mean by that. So it's like 1, 2, 2, 2, and then here we have also 1, 1, 1, 2, 2, 2. I think my board still fits. So, and then here, I'll just write it like that. Here we have element 1, 1 times 1, 1. It should be tensor product, but I'll just trying to save time. So 1, 1 times 1, 2, 1, 1 times 2, 2. So it's boring, but I have to do it because I want to show you how to do the product of those crystals. 1, 2 times 1, 2. 1, 2 times 2, 2. So I will make one intentional mistake here, and your job is to find it. That's what I do often in my classes. Did anybody find a mistake? There is no mistake. I didn't make a mistake, but hopefully I made you think about it. So does it make sense? Like this is just product, like Cartesian product of this set and this set. Okay, so now let's see how the crystal operators act on this thing. So, and just think of it as a word. If we have word 1, 1, 1, 1, how does crystal operate? There is nothing to match, and then you change the last one into a 2. So the arrow goes this way. This is E1 tilde operator. And similarly, it goes this way, and goes this way. And here we have to match like this. So this one goes here, and then after this, it goes here, and this one doesn't go anywhere. Okay, so tensor product of those two crystals separated into those connected components. Each of them is by itself an SL3, I guess, crystal.
I'm a little bit lost. I mean, for that last arrow that you drew, can you just walk us through that in more detail with the
This last
pairing?
arrow, yeah, you just match this 2 and this 1, and now your word is just 1, 2, and you replace the last one with a 2.
Thank you.
Yeah, I mean, thank you for asking. I mean, I want people to ask me questions like that. So okay, so that's how you build a tensor product of those crystals. And there is a more formal kind of rule of how, like, if I define for you what are epsilon and phi functions on crystals, which is not that hard, but it will take time and it's kind of technical. But in this case, we are happy to have this rule which simplifies things. Okay, and then of course, those of you who have studied symmetric functions may recognize this. This is just, this corresponds to taking product of two complete elementary symmetric. So if you take generating function over each of them where each contributes a monomial, right? This is x1 to the 4th, x1 cubed, x2, etc. Then this decomposition is just saying that h2 times h2 is equal to, let's see, does anybody recognize the first guy? I mean, it should be Pierre rule if you know Pierre rule. So the first guy is just h4, right? This is the same crystal we would get if we had just single row of length 4 and we started acting by E1. Is everybody happy with this? And then the second guy happens to be H31 and the, sorry, not H, S, Schur functions. Although H4 was right, so S31 and the last one is S22. There's only one way to fill 2 by 2 square with 1s and 2s, so it's a semi-standard tableau, which corresponds to this only one element, only one vertex in this crystal. Okay, any questions about relation to this decomposition of symmetric functions?
Well, I didn't really follow it. Is it going to be important later on? Because
yeah, it is going to be slightly important. But it's, so is there anything I can help you with to understand this?
well, where did 4 and 3, 1 and 2, 2 come from? I missed that.
So this is just what happened. I mean, that's a good question. They come from us recognizing those components, from me knowing how they would like, because I know how to build a crystal on those shapes, right? So if I have shape 1, 1, 1, 2, the crystal operator takes it to 1, 1, 2, 2, and then it takes it to 1, 2, 2, 2. That's how a crystal, SL2 crystal on shape 3, 1 looks like. And I just recognized that that's this guy. So, right.
So different shapes. So different shapes give rise to different patterns of chains.
That's
in the
right.
crystal.
Different shapes give different. So, and in general, for any shape of semi-standard tableaux, there is crystal you can build on it, and that's. And on the other side, here I just knew what the Pierre rule is, right? I knew how to multiply H2 by H2, how it will decompose into symmetric functions, into Schur functions. Okay, does this help a little bit?
Yes, it does. Thank you.
Okay, any other questions? I really want people to understand everything I'm doing, so don't be shy to ask any question. Okay.
Sorry, so am I right to assume that the leftmost column tells you the shape of the tableau by reading the number of ones as the first row, the number of twos as the second row?
In this case, yes, but in general, I don't think there is such a rule. You just yeah, it becomes a little more complicated. But what it's true, and in fact, that's why people care. One of the reasons people care about crystals so much, because in principle, if you take tensor product of two irreducible representations of SLN or GLN, I mean, it's a little Richardson problem to decompose it into pieces, and this method just tells you how to do it, right? There is some rule by which you start with two crystal graphs. There is some precise rule how you draw arrows on their product. And then you just look at the connected components and you see how it decomposes. So people usually think of it as an efficient way to see how product of two representations decomposes into irreducible representations.
Thank you. That helps too.
I don't know any simple heuristic, just like look at the left column or anything. I think in general, it will be more complicated.
Okay, thank you.
Yeah. Okay, and then one more thing. I'll have to start erasing stuff. So one more thing is that probably don't need this anymore. So there are all those more fancy symmetric functions, right? So there is, for example, there's also something called whole Littlewood polynomials. Which happen to be deformations of those products of H's, right? So it's some Q analog of a product of H's. So in this case, we would write something like whole Littlewood 2, 2, which corresponds to taking this product H2 times H2. And the formula for whole Littlewood 2, 2 is like this. It's S4 plus Q S31 plus Q squared S2, 2. So it's an important deformation of those symmetric functions, products of H's. And people, so the way you get it is that some terms in the product get some power of Q in front of it. And it turns out that it's pretty easy to tell from this picture also which terms get what power of Q. So there's something called energy function. Energy function, which is not that hard to describe, but maybe let's skip it and I'll see, maybe at the end I can tell you what it is. It's easy to compute, I mean, in this case. But it's just some non-negative integer associated to each vertex here. And in this particular case, we would have the following. This would get 0, 0, 0, 0, 0, 1, 1, 1, 2. And it turns, so it's a specific function you can compute on vertices of such tensor product. And it turns out that it's constant on connected components of the crystal. So within one connected component, it always takes the same value. Now here, each connected component got a different value, but in general, it's not true. So there could be some connected components which both get once or something like that. But basically, there is certain function you can compute on such tensor product crystal, which is called energy function. And if you compute it on each of them and you see what power of Q each chunk should get, then you get whole Littlewood polynomial, which is like something many people care about. Any questions about this part? Okay. So far, I'm not talking about geometric crystal. I'm just talking about crystals. And there's one more thing I want to tell you about crystals before I start talking about geometric lifting of all of this. And that's something actually slightly less known maybe than the previous things I told you. It's called R-matrix. So let me try to tell you about R-matrix. But really, if there are any questions, please ask me. Anything at all. So I told you that crystals are supposed to model tensor products of, say, irreducible representations of SLN or GLN. And it's a kind of a silly property in linear algebra that V tensor W is isomorphic as to W tensor V. As vector spaces or as representations if there is action on them. But it turns out that on the level of crystals, this becomes non-trivial. It's still true, but it's non-trivial. So let me explain what I mean by that. So imagine that I want to take tensor product single box times 3 boxes. Right, so previous one I had on the board was 2 times 2. This one is 1 times 3. So I will, here I will write, so, and I can do it in 2 orders. Right? I can also take 3 boxes tensor product 1 box. Okay, I'll just write how it looks like. So here's the first one. 1 tensor, oh, I'll just write product again to save time. 1 product 1, 1, 1 goes to 1 product 1, 1, 2 goes to 1 product 1, 2, 2 goes to 1 product 2, 2, 2 goes to 2 product 2, 2, 2. And then the second connected component looks like this. 2 product 1, 1, 1 goes to product 1, 1, 2 goes to 2 product 2, 2, 2. 1, 2, 2. Okay, so does anybody kind of recognize what I've been doing here? So there is a kind of rows are labeled just by 1 going into 2. And columns are labeled by crystal on 3 things, right? 1, 1, 1 goes to 1, 2, 1, 2 goes to 1, 2, 2 goes to 2, 2, 2. And then this is a Cartesian product. And on it, I have those arrows, which split it into 2 connected components. Okay, so now if I did it the other way around, if I put the factor of size 3 first, it would look like this. And this is slightly painful because, okay, I'll try to do it like this. 1, 1, 1 times 1 goes into 1, 1, 1 times 2, goes into 1, 1, 2 times 2, goes into 1, 2, 2 times 2, goes into 2, 2, 2 times 2. Okay, and the second component looks like this. 1, 1, 2 times 1 goes into 1, 2, 2 times 1, goes into 2, 2, 2 times 1. Okay. And you can see that the 2 chunks, like when we say that those 10 representations are isomorphic, we expect to see the same chunks. And there is indeed a chunk which looks like a chain of size 5 and a chunk which looks like a chain of size 3, both here and here. I don't know, any questions about the picture I drew?
I'm just a little confused by why the 1 gets left alone and doesn't get changed into a 2.
This last one?
Oh, no, never mind. The pairing. Yep, 2
Because
gets
it was
paired with
always
1.
paired.
Yes, I see it. I see it.
Yeah, it just never changes. So, okay, so I claim that you see this isomorphism by seeing that those 2 chunks are isomorphic to each other. This guy corresponds to this guy, and that guy corresponds to that guy. But now if you look at, I don't know, let me pick. Like, let's pick the middle guy in the smaller chunk. Okay, here it's this guy, and here it's this guy. So the key observation is that what we do is not just swapping the 2 factors. The guy who corresponds to this guy over here is not just 1, 1, 2 times 2. It's 1, 2, 2 times 1 for some reason. And that's what I mean that this isomorphism is not trivial. You need, something happens for any product in the original, for any point or vector in the original product, there is a way to swap them and correspond to some vertex in the final, in the other way product. All right, so But this way is not just simple swapping. You need to actually do something inside of them. And this something you do is called R-matrix. And I don't know why it's called matrix. Maybe somebody does, but it's not a very good terminology, but this is a very standard terminology. It's not a matrix, it's just a map, but it's called R-matrix. Any questions? So in this case, like it would send this guy to this guy. And in a couple of seconds, I'll tell you how to do it in this special case in practice, but anybody wants to ask me anything about it before I tell you how to do this in practice?
Well, I have a possibly premature question, but when you have a triple tensor product, are you going to talk about that? Because that's
Yeah,
when
I
you
will
say
talk
R.
about that.
Okay.
Yes, I will talk about that. So in practice, I'll just say it. In practice, the old one and the new one both should Judith-Decan to the same thing. If you know what is Judith-Decan, if you write them like this and try to Judith-Decan kind of into the corner, or if you write it like this and try to Judith-Decan into the corner, they should Judith-Decan to the same thing. And it turns out that for two rectangular factors, it's always unique. So once you require, if you have two semi-standard tableaux of rectangular shape, and you kind of want to swap those shapes, but you want the product to still be, semi-standard tableaux which Judith-Decan to the same thing as the old pair, there is a unique way to do it. And this unique way is R-matrix. Okay, so and now what Jim was asking, at least I think it was Jim. Was it Jim?
Yeah, that was me.
Yeah. So something really neat happens if you start looking in more than two factors. So what starts happening is that you get braid relation, right? So imagine now that we took product of 3 crystals. Then you can first swap those two, shapes. But which I mean, like for any filling of this guy, you can find unique filling of this guy. And then you swap those two, and then you swap those two again, and etc. So you arrive to them in the opposite order. Or you could have gone the other way around. You could have first swap those two, then those two, then those two. Each time you swap, what I mean is that there is some semi-standard filling, and you apply this R-matrix to those two factors. And it turns out that it satisfies the braid relation. So in fact, R-matrix gives an action of the symmetric group, and Gabe will talk probably about this action. So the R-matrix gives an action of the symmetric group on this stuff. Okay, any questions about, yeah, let me just say that. Okay, I'm about to start geometrizing all of this. But before that, any questions at all about, it's a very neat property, and it's not easy to prove property. In fact, I don't know, for just general 3 rectangles, I don't know, I don't think I know elementary proof of this property, that the braid relation is satisfied by R-matrix.
Pasha?
Yeah.
I realize that they're not the same, the shape or length, but is there some way to think about this R-matrix in terms of RSK?
Yeah, you could, instead of talking about Judith-Decan, you can think of RSK. But
Okay.
if you ask, so that's how you can define it. You can say that if you RSK insert the second factor into the first factor, and you do the same thing here, the result should be the same.
Okay. I just usually with RSK, I usually think of them as being of the same shape, and here they're different lengths of rows.
Right. So and it's important, if they were the same length, then R-matrix would be trivial.
Sure.
Because if you have 2 tableaux of the same shape, and you want to swap their shapes, and you wanted to Judith-Decan to the same thing, then there's obvious solution, which is trivial, which is just leave them the same as they were. Right. So yeah, you just need to think about those 2 things as kind of inserting this guy into this guy. And if you think about it this way, then it doesn't matter that they're different shape. Okay, any other questions? Okay, so let me start showing you how to geometrize all of this. And so I will not tell you right away what is geometric crystal because it's painful and unilluminating. I could tell you at the end if you want. But I didn't tell you what a normal crystal is either. I just gave you, told you who to construct it. So maybe that's okay. So, but here's what we're going to do. Think of our single row crystal as just an n tuple of numbers. I have x1 ones, x2 twos, xn n's. So I correspond to it vector x1, x2, xn. And then instead of thinking of those as having to be integer numbers, I will think of them as just being real numbers. And now I will try to act by operators, crystal operators on this thing. So I will have geometric crystal operators. And here's a kind of a bit of a technicality which is important to understand. What we will be acting on, so operator EI tilde will take a real or a complex number and some point in the crystal, and it will produce another point in the crystal. So what do I mean by that? We will have additional parameter. We will have EIC. Let's just forget tilde. Where think of the C as now it will be a real number, but it's kind of meant to correspond to how many times we apply crystal operator in the piecewise linear world. So in piecewise linear world, we always tend to think about it as just applying the crystal operator once. But we could define more general crystal operators, EIC, where C is an integer, where it's just operator which applies EIC times. So it's those guys whom we will geometrize. We will say EIC now, where C is a real number, will act on such columns.
Okay, I have another possibly premature question, which is that since you've defined your maps EI to be non-invertible because eventually you apply it too many times, you get 0, C can't really be a negative number here, can it?
It can be, because in geometric world, it's always defined. So
you'll explain that later, I hope, because I don't see it.
So that's right. So, and there is something called decoration function, which in piecewise linear, so let me tell you about this at the end, okay? I mean, it's a weird difference because in geometric world, you can always act by crystal operator, but some course, yeah, let me tell you about this at the end, okay? It's an interesting question. But now I just want to just define the basic definition. So if it takes vector x1, x2, etc., xn, what does EIC do in tropical world or piecewise linear world? It decreases, xi by 1 and increases I plus 1 by 1, xi plus 1, right? It makes number of I smaller by 1 and number of I plus 1 bigger by 1. Everybody understands that? So in geometric world, this corresponds to just, let me try it like this, x1 through xi plus 1 through xn. So in geometric world, we will multiply xi plus 1 by c, and we multiply xi by c inverse. So the only thing is that it has to be not 0. So the only requirement on this parameter c is that it's not 0. Okay, I want everybody to understand that this tropicalizes the action I showed you before, right? So instead of adding 1 and subtracting 1 from xi and xi plus 1, it multiplies xi plus 1 by c and divides xi by c.
So it seems to me that your variables are actually the exponentials of x1 through xn.
Sort of, but I mean, it's something which happens when you detropicalize in general, I think.
But I'm thinking you should be living in the orthant, and you're saying you're not.
In an orthant. ortho. No, you don't have to live in ortho. In fact, this definition often is made just over C. And they are complex numbers. And again, the only requirement is little c is not 0. So they would say that little c is element of the torus. Like once you poke out 0 from complex plane,
Okay.
they call it torus. Okay, but disregarding those technical kind of skepticism about how it should be defined, is this definition clear? And now, just like in the piecewise linear world, we can extend this action on the single thing to action on tensor products, right? So you think of it, maybe, I wish I had more space. But let me try to write it in small here. So let's say we have several such columns, which I could denote by a matrix, which is not 1 by n, but several by n, like x1, 1, x2, 1, x3, 1, and x1, 2, x2, 2, x3, 2. And now I want to act by crystal operator E1C here, or as a rows. And what I want to do is, like in my head, I think of this as being analog of this tensor product. There are some 1s, there are some 2s, there are some 3s, there are some 1s, there are some 2s, there are some 3s. And there's, x1 1s here, x2 1s here, x1, x, whichever it is, x1, 2 1s here, etc. So, and now I want to act by crystal operator E1 on this tensor product. And again, something interesting happens here, because in the piecewise linear world, the rule for action on tensor product is that only one of the factors changes. And the whole trickiness is just which one to choose. Somehow, if you look at Kashivara's definition of how it works, then only one of the factors will actually get acted upon in piecewise linear world. And there's action will be kind of what you just have inside this one single little crystal, single row crystal. But in the piecewise linear world, all of the factors change. Somehow there's a rational transformation you end up applying to.
Pasha, did you mean to say in the geometric world, everything?
Yeah, in geometric world, right. So let me just show you what will happen here, how the formulas look like. And then I can say something about the rule, how those formulas are obtained. So in this case, and again, think of it as like tensor product between those two little columns, right? So this column tensor product, this column, I can write it this way, maybe if it's easier. So the crystal operator will act on both factors, and it will act on both factors with some parameter. So C1x11, I guess I should write inner C1x12, and then the 3's don't change, just like in the usual crystal. If you act by E1, 1s and 2s change the numbers, but 3's and everything else stays the same. So this one still will be x13. And here I have C2 inverse. Well, let me just write C2. And here I'll write inverse because that's what I have in my notes. C2 inverse. X12, X22, X32. So what happened here? This crystal operator acted on this guy with parameter C1 and on this guy with parameter C2. And I only need to tell you the formula for those C1 and C2, and they look something like this. C1 is Cx12 plus x21 divided by x12, x21. And there's a similar formula for C2. The product of them should be just C. So in what sense is this a geometrization of what happens in tropical world? In the tropical world, this little c is always 1. right? That's our single crystal operator. And when we split it into two chunks, here the product should be C, but there in tropical world, the sum should be C. So what non-negative numbers add up to 1, integers? It has to be 0 and 1. So in the piecewise linear world, one of those C1 and C2 will always be 0 and the other one 1. And that's why in piecewise linear world, it always looks like our crystal operator just acts on one of the factors and leaves the others the same. Because in some sense, it's just the parameter of action on all others is 0 and parameter of action on one of them is 1. But in geometric world, it doesn't work like that anymore. There is a parameter with which it acts on first factor and the parameters with which it acts on the second factor. And there's some rule, which, I mean, this looks kind of complicated, but again, there are precise rules. It just would take time to show you where did I get those formulas, etc. And it's an interesting exercise to tropicalize this and to actually check that you indeed get the action I was telling you in the piecewise linear world. It can be done. You can just stare at those formulas enough and you can see that they tropicalize to the rule we had for action on those guys. Okay, I have 1 minute left. Any questions? Any questions I can answer about this? So the thing I didn't get to tell you to do is there's also such thing as R-matrix, which is a rational transformation. You can think of it as swapping those two columns, but it doesn't just trivially swap them. It does something funny. Like there are rational functions which appear as entries. And this is called birational R-matrix usually in the literature. Okay, so Gabe will be talking a lot about this kind of actions on rectangles. Like this is like 2 by 3 rectangle, and he'll be talking about acting by crystal operators on those rectangles, etc. I suspect he will. So there are actually 22 chats which I didn't look at.
I have a question.
Okay.
So the piecewise linear crystals came from the Q to 0 limit of quantum group representations.
Yep.
But these ones, where do they come from? Are they just defined as like these transformations?
Geometric crystals were defined by Berenstein and Kazhdan, and they are something which lives inside algebraic groups. And I don't know, Gabe, do you know how to answer this question? Like, where?
Well, I'm gonna explain how you get these types of rational functions from stuff going on inside the algebraic group. In this case, it would be GLN. So that's maybe the best answer that I know.
That's right. So, yeah, I mean, I think it's sort of hard to explain motivation for Berenstein and Kazhdan work, except that maybe, I mean, from my combinatorialist point of view, there is this wonderful combinatorics of RSK, Jodeta-Khan, and for me, crystals is from the same kind of area. And they really figured out how to lift this combinatorics to geometric setting in exactly the same sense as, people in this workshop lift things to geometric setting. So you just didn't get to see enough of those miracles, how something, for example, Gabe will probably talk about geometric RSK, and I actually wanted to show you how it works, but I don't have time. But it's amazing to see how those rational formulas tropicalize to an algorithm, right? We have RSK algorithm, but geometric RSK is not an algorithm, it's just a bunch of formulas. But nevertheless, it sort of gives you the same answer once you tropicalize.
I see, thank you.
Yeah, and just to answer Jim's question, so in this geometric world, you can go on forever, like meaning you can keep acting by those ECs and there is no limit. So the way Berenstein and Kazhdan dealt with it was they introduced something called decoration function. So what was it? So for this kind of simple crystals, the decoration function would be just x1 plus x2 or rather, let me say it like this, minimum of x1, x2 through xn. And they say that you cut around your crystal so that this decoration function never becomes negative. Okay, so that's their way to deal with it. But in the rational world, this would correspond to some kind of decoration function, which in this case would be just x1 plus etc. plus xn. And of course, in rational world, it doesn't cut anything. There's no minimum anymore. But what people do, people write integral. People write integral of a geometric crystal, and they put this thing, exponent of this thing. And those integrals are analogs of Schur functions. They're so-called Whittaker functions. And you put something like this, minus this decoration function over here, d whatever, some measure. And the way it works is that the bigger this thing is, the smaller this factor is, the less you count this thing. So in the geometric world, decoration function discourages certain points. It discourages certain points where this is too big, because they will contribute to Whittaker function very little. While in piecewise linear world, decoration function is much more strict. It forces you to just not consider anything where it's negative. Okay, I don't know if this might make any sense, but
It's interesting.
okay. Yeah, I think so. Yeah, Whittaker functions are interesting.
Okay.
Okay, I'm out of time. I should probably give turn to Ivar.
Thanks so much for that talk. I especially liked, Pasha, that when we could see you writing on the board, we could also see you, the image of you writing on the board, and so on. Like it goes to infinity, just like these, E1Cs in the geometric setting. So
Yeah, I was just thinking about the reflection of the screen, and like I thought that there's nothing I can do about it. It's like this joke where little kid is asked what is rabies and what can be done about it, and he says rabies is a Jewish priest and there's nothing you can do about it. So there was nothing I could do about this reflection of.
yeah. I would like to say it's no reflection on you, but in fact it was. So let's see. Sorry about the dog fest here. So Gabe, are you ready to go?
Wait, I was going to
Yeah,
do
but-
questions for Pasha's talk, and so that will just take a few minutes, and then I don't know, we could even go back to geometric R matrices if he wants to say more about that after, but we can see. Okay, yeah. So
Sadly, I have to go, but I have like 3 kids to take.
Oh, sorry. Yeah. Okay. Thanks, Pasha. Okay, cool. So yeah, I just wanted to maybe just, I think probably a lot of people here already know this story, especially about the classical crystals or crystal crystals, as Pasha was calling them. So yeah, so on this side, I just had a quick summary of, so thinking about these combinatorial crystals or the piecewise linear world, as he said. So yeah, the way they arose, introduced by Kashiwara and Lustig, is in the study of representations of Lie algebras and their quantum groups. So they were originally introduced as combinatorial models for Lie algebra representations. And so more explicitly, if you have a Lie algebra, which I denote curly G here, and consider its quantum group, so with a quantum parameter Q, then if you look at the representation, so a vector space with an action of this quantum group, then a crystal can be thought of as a nice basis for this representation at the setting where the quantum parameter is 0. So as Pasha was explaining, so we have some finite set or the set of vertices in the graph, and then the Kashiwara operators, which correspond to the Chevrolet generators of the Lie algebra, so the raising and lowering operators, as well as a weight function, which is keeping track of the weight of the elements. And so in the graphs that Pasha was drawing, so the vertices were elements of this finite set, and then the edges, he was drawing the E's, I guess. So the edges were the labeled
Well,
by.
Pasha was swapping what E's and F's typically are in his picture.
Yeah, so his E's are my F's, sorry. Yeah, so the F's are going down in this language. And so Pasha was talking about so a model for when we take the Lie algebra to be SLN. So one model for such crystals can be realized as semi-standard Young tableau. So if you fix some partition lambda with at most n-1 rows, and you consider all the semi-standard Young tableau of shape lambda, this is a crystal for the representation for SLN with highest weight lambda. And so he was considering just a single row, but in general, you can think about any partition. Yeah, so then he described the R matrix, which gives you a commuter on crystals. So this swapping of the tensor product, and it satisfies the braid relation. So pictorially, one can visualize it this way. And yeah, so this gives the, if you think about the whole category of crystals and maps between them, this gives it the structure of symmetric tensor category, or namely, there's an action of the symmetric group on tensor products. And so now on the geometric side, so geometric crystals were defined by Bernstein and Kazhdan. They were defined for an arbitrary reductive group. So I guess in Pasha's talk, they were mostly for SLN. And so I think part of their motivation was to study actions of the Val group. So for GLN, that's just the, or for SLN, that's just the symmetric group. So by rational actions of the symmetric group, so realized through rational functions. And I think this is probably something Gabe will touch upon in his talk as well. So for instance, given a geometric crystal for m by n matrices, so thinking about the GLM geometric crystal, this gives us this produces a action of the symmetric group on this space via the geometric R matrix, which unfortunately we didn't get to in Pasha's talk. So yeah, and so these geometric crystals are, if you tropicalize them, namely if you replace in the operations he was talking about, plus product and division by min, plus and minus, and set that real number C to 1, this recovers back the operators on combinatorial crystals. So just to look at the example that Pasha was describing, so this is the GL3 or SL3 crystal for this particular representation. So remember, this was just pairs of one row tableau with 1s, 2s, and 3s in that order. And so what does it look like on the combinatorial side? So right, one way to describe it more explicitly, so the tensor product rule that Pasha was referring to is in this way. So take this bivector or tensor product of two vectors, and you can replace it. So this is what the C1 and C2 look like in the combinatorial world, so completely explicitly. So if you do this replacement on the geometric side, you recover exactly the combinatorial crystals. Okay, yeah, so I think I'll stop here and let Gabe continue with invariant theory for crystals, maybe after a break or.
So we've got a break coming up before the next talk, and people are certainly welcome to continue discussing things during that. Does anybody have any questions for Eva?